Hi, I am Sufyan Latif from the Ohio State University, and I am here to talk about our paper on introducing differential privacy mechanisms for mobile app analytics of dynamic content. Software analytics has been an integral part of mobile app development nowadays. The app developers use analytics to collect information about how the users interact with their apps. Analytics can reveal trends and information accessed frequently by the users. This is usually done using the app analytics infrastructures like Firebase Analytics, Google Analytics, Facebook Analytics, or Yahoo Analytics. Our work is based on Firebase as it is the most popular analytics framework. Analytics data can be used to infer sensitive information. For example, it can be used to determine the political inclinations of an user by tracking what kind of articles she shares on social media. It can be easily misused by the app developers or infrastructure providers like Google and Facebook. Even when they protect the privacy of the collected data, some rogue employees or contractors may do otherwise. Sometimes the data may be shared with government agencies or leaked in data breaches. In our paper, we propose a data collection scheme with built-in privacy guarantees, which would benefit the app users by providing well-defined privacy protection for their data, the app developers who can claim with confidence that they provide privacy by design, and also the analytics providers who can guarantee that the data collected through their infrastructures has privacy protection from the ground up. The privacy guarantees are ensured through differential privacy, which is a rigorous theoretical approach used for privacy-preserving data collection. Differentially private schemes add noise to the data to hide individual data points but still provide accurate statistics of the population. There are prior work that can achieve differential privacy for coverage information of app GUI screens, which assumes a previously known set of entities to be protected. But our work considers a new and more challenging problem. The app contents are not known ahead of time. The contents may vary across different users, time, or location. We have designed a novel differentially private data collection scheme for that. The second challenge is to modify and maintain the app code to ensure privacy. We used automated code rewriting to add a privacy protection layer into the application code. The third challenge is evaluating the privacy versus accuracy trade-offs. The privacy parameters of the scheme can affect the accuracy of the collected information. We used automated testing of applications to observe the effects of different privacy settings on accuracy. Since our implementation is built upon Android apps that use Firebase Analytics, I am showing an example for Firebase, but this also applies to similar analytics frameworks. There are multiple users of the app. When a user opens the app, it loads a set of content items from a remote server. This set of contents retrieved by each user is essentially different. The user may interact with some of these items. For example, the app may present a list of news articles and the user may interact with an article by marking it as favorite. When the user interacts with an item, the event is reported to the analytics server. The analytics server then counts how many times each content item was interacted with by some user and provides a histogram to the app developer. Here the items are shown using integer identifiers. For example, user 1 receives items 1, 3, 4, 6, 7, and 9. Among these items, she interacts with items 1 and 6, and these two events are reported to the analytics server. Our scheme adds a differentially private layer into the app code. It contains a local randomizer that creates a randomized set of events to report. The randomizer takes in both the set of retrieved contents and its subset of items the user interacted with. Then it creates a randomized response, where every content items may be included with some probability. But the items the user interacted with have a higher probability of being included. For example, user 1 interacts with the items 1 and 6 and they are included in the randomized response along with items 4 and 9. The randomized response is reported to the analytics server along with the set of contents retrieved by the user. The app developer can get an estimate of actual frequencies by post-processing the histogram from the analytics server with the probability used for randomization. The goal of this randomization is to ensure that an observer of the randomized data cannot conclude with high probability whether a certain user interacted with a content item or not. Each item the user interacts with is included in the report with some probability p. Each of the items retrieved but not interacted with by the user is also included in the dataset with probability 1 minus p. The value of this probability p is based on the trade-off between accuracy and indistinguishability. The higher value of p ensures more accurate estimation, whereas a lower value would provide more privacy. To develop a proof of concept of this scheme, we created a differentially private wrapper around the Firebase Analytics library and added it into the application code through automated code rewriting. The add wrapper is used to intercept three types of events. Initialization: the wrapper is initialized where Firebase Analytics is initialized. Content retrieval: the wrapper records the content items retrieved by the app. And event reporting: the places where Firebase reports the events of interest. The wrapper creates a randomized set of events and reports it instead. We tested our implementation by simulating user actions using Android UI Automated tool on 9 apps. The test script scrolls through the list populated by retrieved content items and interacts with random items from it. The automated test was performed 100 times over a few days to ensure diversity of the contents. Additional user data was synthesized from it by merging random pairs of users to simulate more users. We measured the accuracy of this scheme using relative error, which is defined as the cumulative difference between the true and estimated event frequencies normalized by the sum of true frequencies. The charts show the result obtained by probabilities 0.75 and zero point 0.9. It is evident that larger values of p improves accuracy of the estimate. Another observation is a significant reduction in error with more users. Most apps have at least 10,000 users, and we observed that with 10,000 users, the error is less than 5% for every app. In conclusion, privacy of analytics data can be ensured with differential privacy. Differential privacy can be introduced via automated code rewriting, and our proposed differentially private scheme can protect data privacy, maintaining a high level of accuracy with large number of users. Thank you for your attention. If you have any questions, please let us know by email.